Welcome to the deep dive. Today we're looking at the hidden forces inside, well, pretty much everything around us. Ever wonder how some structures just work, how they hold up?
Yeah, it often comes down to how they handle multiple forces at once, not just one push or pull, but a combination.
Exactly. And that's our topic today. Combined loadings in engineering. We're diving into how different forces interact within materials. Our mission here is to really get you up to speed on how engineers figure out the stresses inside critical parts, think uh, big pressure vessels or structural supports.
Right.
How do they cope with several loads simultaneously? We want to give you that understanding, maybe uncover a few surprises too.
And we'll see how fundamental ideas explain why complex things like maybe a ski gondola support or a simple gas tank actually stand up to the job. It's about the why it matters behind the math.
Okay, let's get into it then. First up, thin-walled pressure vessels. Sounds specific. So what exactly makes a pressure vessel thin-walled in engineering terms?
Well, it's defined by a ratio. You look at the inner radius r and compare it to the wall thickness, t. If that ratio r over t is 10 or more, we call it thin-walled.
10 or more. Okay, why that number? Is it just arbitrary?
Not at all. It's a threshold that lets us use a much simpler way to calculate the stresses inside, and it's surprisingly accurate. For a ratio of 10, the prediction is only about 4% off the actual maximum stress.
Ah, okay.
And as that ratio gets bigger, meaning the wall gets even thinner relative to the radius, the error gets even smaller. Oh, and usually when we talk pressure, we mean gauge pressure.
Right, the pressure above atmospheric. Got it.
Mm.
So where do we typically find these? Are they common? And I've always noticed gas tanks often have those curved ends.
Yeah, the hemispherical caps.
Exactly. Why is that? Does it help?
Oh, definitely. You see these vessels all over.
Yeah.
Boilers, large storage tanks, like you said, gas tanks. And yes, those hemispherical ends are a smart design. It relates to the stresses in cylindrical vessels. See, in a cylinder, under internal pressure, there are two main stresses we look at. First is the circumferential stress, sometimes called hoop stress.
Hoop stress, like trying to burst the hoop?
Precisely. It acts around the circumference, trying to split the cylinder open along its length. The formula is sigma 1 equals PR over T. Pressure times radius divided by thickness.
Okay, PR over T in the second
That's
case.
the longitudinal stress or axial stress. It acts along the length of the cylinder, trying to pull it apart end to end.
Makes sense.
And its formula is sigma 2 equals PR over 2T. Same factors, but divided by twice the thickness.
Wait, hang on. PR over T for hoop and PR over 2T for longitudinal.
Exactly.
So the hoop stress is double the longitudinal stress.
You got it. That's the key takeaway. The stress trying to burst the cylinder around its circumference is twice as big as the stress trying to pull it apart lengthwise.
Wow. Okay, that seems important.
It's very important for fabrication. It means any seam or weld running along the length of the cylinder has to be designed to handle twice the stress as a weld going around the circumference.
Right, because that's where it's more likely to fail. I think I read about a pipe bursting exactly that way along its length.
It happens. That higher hoop stress dictates the failure mode under pressure. Now, compare that to spherical pressure vessels.
Okay, spheres. How are they different?
The analysis is similar, but the result is simpler. In a sphere, the stress on the wall is the same in all directions. It's uniform.
Uniform. So no hoop versus longitudinal.
Nope, just one stress value. And interestingly, the formula for that stress is sigma equals PR over 2T.
PR over 2T. That's the same as the longitudinal stress in the cylinder.
Exactly the same magnitude.
Huh.
Right. We should mention a limitation here. This thin wall analysis mostly ignores the radial stress, the stress acting through the thickness of the wall itself.
Why ignore it?
Well, it's usually much smaller than the hoop and longitudinal stresses.
Mm-hmm.
Like for that ratio of 10, the hoop stress is 10 times bigger than the maximum radial stress. So for thin walls, we often just focus on the bigger stresses.
Makes sense. Focus on the biggest threat. What about pressure from the outside?
Good question. External pressure causes compressive stresses. Instead of bursting outward, the vessel might suddenly collapse inward or buckle. That's a different kind of failure related to stability.
Okay, so let's bring this together with an example. Imagine we have a cylindrical tank, say 1.2 meters inner diameter, 12 millimeter thick wall, and a spherical tank of the same size and thickness.
Right.
If the material can only handle, let's say, 140 megapascals of stress, how much pressure can each hold?
Okay, doing the math. For the cylindrical one, the limiting factor is the hoop stress, right?
Yeah.
Sigma 1, which is PR over T. So 140 MPa equals P times 0.6 meters divided by 0.012 meters. Solving for P gives you 2.8 megapascals.
2.8 MPa for the cylinder and the sphere.
For the sphere, the stress is uniform, PR over 2T. So 140 MPa equals P times 0.6 meters, divided by 2 times 0.012 meters. Solving that gives 5.6 megapascals.
Wow, 5.6 MPa, that's exactly double.
It is, and that's the big takeaway. Even though spheres might be harder to make, for the same material and same maximum stress allowed, a spherical vessel can withstand twice the internal pressure as a cylindrical one.
That's fascinating. Just changing the shape makes it twice as strong in that sense.
Geometry is powerful in engineering.
Okay, so that covers pressure vessels. Let's broaden the view now to more general combined loadings because, like you said, things in the real world rarely see just one force.
That's right. Think about a bridge beam or machine part or, yeah, that ski gondola support again. It might be bent, twisted, pulled, and compressed all at the same time.
So how on earth do engineers figure out the total stress? This sounds like it could get incredibly complicated.
It can seem that way, but there's a really elegant principle that helps enormously. It's called the principle of superposition.
Superposition. Okay, what's the core idea?
The core idea is surprisingly simple.
Hmm.
If the material behaves nicely, specifically, if it's homogeneous and linear elastic.
Linear elastic meaning it springs back, and stress is proportional to strain.
Exactly. And if we're not too close to where the load is applied or sharp corners, that Savinon's principle, then we can calculate the stress from each individual load separately and then just add them up algebraically at any point we're interested in.
Add them up, just add the numbers.
Pretty much. Normal stresses add to other normal stresses. Shear stresses add to other shear stresses. It allows us to break down a complex problem into simpler pieces.
Okay, that sounds manageable. But how do you find those individual stresses first? What's the process?
Right. There's a procedure. Step one is figuring out the internal loadings at the specific point, or usually the cross-section you care about.
Internal loadings? You mean like forces and moments inside the material?
Precisely. You imagine cutting the object at that point. Then you use basic equilibrium. Sum of forces equals 0. Sum of moments equals 0 to find the forces and moments acting on that cut surface. Typically, you'll find an internal normal force, pulling or pushing, a shear force, trying to slice, a bending moment trying to bend it, and maybe a torsional moment trying to twist it.
And these act at the centroid you mentioned.
Yes. The forces are considered to act through the centroid, the geometric center of the cross-section. And the moments are calculated about axes running through that centroid.
Okay, so you've cut it, found the internal forces and moments. Step 2 must be turning those into stresses.
Correct. Each internal loading creates a specific type of stress distribution. The normal force, N, causes a uniform normal stress. Sigma equals N over A. Force divided by area. Simple push or pull.
Okay, N over A. Got it.
The shear force, V, causes shear stress. Tau equals VQ over N. That formula is a bit more involved, depends on the shape.
Right, the shear flow idea.
The bending moment, M, causes normal stress that varies linearly. Sigma equals minus My over I. 0 at the middle, neutral axis, max at the top and bottom.
My over I. That's the flexure formula.
Yep. And the torsional moment, T, in a circular shaft, causes shear stress. Tau equals TOOO over J0 at the center, max at the outside surface.
TOO over J, the torsion formula.
And of course, if it's a pressure vessel situation, you'd also include those pressure-induced stresses, sigma 1 and sigma 2 we talked about earlier.
So you calculate all these individual stresses potentially acting at your point of interest.
And then step 3 is superposition. You just add them up, add all the normal stresses together, paying attention to tension versus compression, positive versus negative. Add all the shear stresses together, paying attention to direction.
And that gives you the final combined state of stress at that point.
Exactly. You can then draw it on a little stress element to visualize what the material is experiencing right there.
Let's make this concrete. Can we look at some examples? How does this play out in practice?
Sure. Imagine a simple rectangular post. If you push down right on the edge, not in the center.
An eccentric load.
Right. That single force actually does two things internally. It creates an internal normal force, compression N, and also an internal bending moment, M, because it's off-center.
Ah, okay.
So at any point in the post, the total normal stress is the sum of the uniform compression, NA, and the linearly varying bending stress, now my I. One side gets compressed more. The other side might even go into tension if the load is eccentric enough.
So the bending part can actually reverse the stress on one side.
It absolutely can. Another example, that gas tank again. Say it has internal pressure and something heavy is sitting on top, pushing down.
Okay, combined pressure and axial load.
At a point on the side wall, you'd have the hoop stress, sigma 1 prif, from the pressure, You'd also have longitudinal stress, sigma 2, but that sigma 2 is now a combination of tension from the pressure, P2T, and compression from the external load, force area.
So you add the tension and subtract the compression to get the net longitudinal stress.
Precisely. The point ends up being pulled in one direction, circumferentially, and pulled or pushed in the other direction, longitudinally. That's biaxial stress.
How about a beam with a load spread across its top?
Good one. A point on the top surface would experience compression from the bending moment, right?
Yeah.
And maybe some normal stress if there's an overall axial force, but usually zero shear stress right at the top surface.
Okay.
But a point on the neutral axis, the center line of the beam, it experiences zero bending stress. But it will likely have normal stress from any axial load, and it will experience shear stress from the internal shear force, they. It's often where shear stress is highest.
So different points in the same object can have completely different combinations of stress.
Totally different. That's why engineers need to check critical points, often corners, points furthest from the neutral axis, points on the neutral axis, etc.
This leads to something interesting. You mentioned that eccentric load potentially causing tension. What if you have a material that can't handle tension, like stone or concrete? How do you load it safely?
That brings us to a classic concept, often called the middle third rule for rectangular cross-sections, or the idea of the kern for general shapes.
The kern.
Yes, it's the central region of the cross-section. If you apply a compressive load anywhere within this kern, then the entire cross-section will remain in compression. No tensile stress will develop anywhere.
How does that work?
Well, the eccentric load creates compression, Na, and bending, Ia. For a rectangle, if the eccentricity E is small enough specifically, less than 1/6 of the dimension in that direction, like h bix if the height is h, the compressive stress Na will always be larger than the maximum tensile stress caused by the bending moment at the edge.
So the compression always wins over the potential tension.
As long as the load stays within that middle third, yes.
Why is that rule so vital?
Think about ancient stone columns or brick arches or even modern concrete foundations. These materials are great in compression, but terrible in tension. This rule ensures they don't crack. Engineers designing these structures have to make sure the load path stays within the kern to prevent tensile failure. It's fundamental to masonry and concrete design.
A simple rule with huge implications for structural integrity. That's really neat.
It really is a practical design guideline born directly from understanding combined stress.
And it's amazing to see how these same principles apply across the board, not just big structures, but bones, tools like pliers or clamps, even a simple signpost reacting to one load. It seems like this combination of forces is just everywhere.
It truly is. Once you start thinking in terms of combined normal stress, bending stress, shear stress, torsional stress, you see them interacting in almost everything that carries a load.
So we've gone from basic stresses in pressure vessels, seeing how shape alone dictates strength, to this powerful principle of superposition that lets us tackle complex combinations of forces.
We really covered how engineers can break down these interactions, bending, twisting, pulling, pressure, calculate the individual effects, and then recombine them to understand the full picture.
It provides a clear framework for analyzing real-world complexity.
Definitely.
Yeah.
So maybe a final thought for everyone listening. Next time you look at, I don't know, a chair leg, a bicycle frame, a shelf bracket,
Yeah.
anything really,
Yeah.
just take a second and think, what forces are acting on this? Is it being bent, twisted, pulled? Probably combination, right? How do the engineers use these ideas of superposition and stress analysis to make sure that simple object does its job without failing? That hidden world of stress and strain is operating constantly, all around us.